Ladies and gentlemen, welcome to the 12th series of INA IGS Geosynthetic webinar under the theme, Why is Geogrid so difficult to model in finite element analysis? This event is brought to you by the Indonesian chapter of the International Geosynthetic Society, or INA IGS. My name is Rifa Nurkayungyun, and it is a pleasure to act as your master ceremony in this event. Before we start, allow me to read the rundown of our event this afternoon. First, I will be reading the rules of the webinar. Second, there will be an opening remarks by the President of INA IGS, Bapak Budianto Wijaya. After that, the event will be guided by Bapak Michael Lobby as our moderator to start the presentation of our speaker, Andrew Lees. The event will then continue with a Q&A session. We would like to ask you to stay with us until the end of the event because we will be doing a quiz with a total of 250,000 rupiah for 2 winners. We will also give you access to the e-certificate at the end of this webinar. Ladies and gentlemen, for your own convenience, please put attention to the following rules. You can submit your questions for the speaker through the Q&A feature located at the bottom of the screen. The question should be in English. You can raise your question before, during, and after the presentation of the speaker. We expect you to stay with us until the end of the event to get the information you need for the gates and also the soft copy of the presentation from the speaker. This event is also live streamed on INA IGS YouTube channel, or you can directly go to the link bit.ly/INAIGS12YT. If you have a question, be shown on the chat. Now, without further ado, I'd like to invite the President of Bapak Budianto Wijaya to give his opening remarks. To Bapak, time is
Good evening, ladies and gentlemen. As the President of INA IGS, I warmly welcome and thank Dr. Andrew Lees as a speaker in our monthly webinar. Today is the 12th webinar organized by INA IGS and the last webinar in the year of 2021. The target of this webinar, as we always strive to, is to share the knowledge and experience in geotechnical engineering, especially in geosynthetics. Hopefully, the seminar held will nurture deeper understanding of geosynthetics and becoming one of the go-to sources for geotechnical engineers. The kick-off seminar in 2022 will be held in February. I would like to express my sincere gratitude for the hard work of our webinar division led by Mr. Krisandi Saptianto and his team for a continuing success of INA IGS seminars. Next year, INA IGS will celebrate its 30 years birthday, and to celebrate the milestone, we are going to invite all of you to attend the conference in November 2022. We also note the rising need of industrial knowledge and applied engineering for university students and eager to be part of contributing partners. Kindly contact our secretary should your university are looking forward to have insightful and experienced engineer to share their expertise. It will be an honor to be partnered with universities all over Indonesia. I thank you for all our members and especially for all INA IGS committees which help and bring INA IGS to be a better, respected, and prominent organization. On behalf of INA IGS, we welcome you all and wishing a Merry Christmas to those who celebrate and brighter and prosperous Happy New Year to us all. Thank you.
Thank you, Bapak Budi, for your kind remarks. To all audience, we invite you to join INA IGS as individual members by registering yourself through the link bit.ly/member INA IGS. Ladies and gentlemen, now this webinar will be guided by our moderator, Bapak Michael Dobi. Before I give the floor to Bapak Michael Dobi, I would like to remind you that you can start submitting your questions from now, during, and after the presentation by using the Q&A feature. We would also like to remind you to stay with us until the end of the event to get the information you need regarding the e-certificates and also the soft copy of the presentation from the speakers. Now, please welcome our moderator, Bapak Michael Dobi. To Bapak Michael Dobi, the time is yours.
Thank you very much, Rifa, for your very, very clear and precise introduction. We've reached a special occasion today, as Pak Budi mentioned, the 12th of our webinars of this year, 2021. I think it's been an incredible series of events we've had. We've heard some incredibly interesting webinars and presentations, and I think you'll see today that we'll be carrying this through right through to the very end of this series of webinars. So I would especially, before I introduce our speaker, I would like also to thank all participants who take part and listen to these webinars. And I certainly hope that you've gained a lot of interesting facts and knowledge from these events. I believe we've covered a huge amount of topics and material in the last 12 months. And that will certainly continue tonight. I'd also like to echo Pak Budi's words of thanks to our organizing committee of INA IGS, who look after these events. They send out the invitations, they arrange the Zoom practices and everything we do to try to make these run as smoothly as possible. The only problem we sometimes have is the internet. So I hope the internet is helping us tonight to give you a nice, clear presentation of this webinar. So I now would like to introduce our speaker tonight. As you've already heard, Dr. Andrew Lees. And in fact, Andrew is my colleague at Tensar, in fact, for the last 6 years or so. And in fact, Andrew is originally from the UK, he's British, but in fact, for the last 16 years, he's been living in Cyprus. I'm not quite sure how well known Cyprus is in Indonesia, but maybe it's something you could Google to find out exactly where it is. But anyhow, he's not that close to us, but he's a bit closer than somewhere like the UK when it comes to his time zone. He also set up a company called GeoFem, which you'll see is mentioned there below his name, which is a company that specializes in using numerical techniques to assist in geotechnical and other civil engineering projects, as well as other techniques as well. I think there's a whole interesting webinar we could hear for other things that GeoFem do, but tonight we'll just be hearing from Andrew. Also like to mention that Andrew is only our second non-academic speaker this year. All others have been academics, mainly professors or similar. However, what's very nice is that we have someone speaking tonight who is working in our industry. He does have earlier experience working in the academic field, but you'll see how he's, if you like, combined that sort of deep knowledge of a particular topic and is now applying it into practice, which I think is something really exciting. So Andrew has a deep knowledge and experience in finite element analysis, numerical modeling. And what I've seen over the last 6 years is how we have benefited from this knowledge. We have many colleagues now who've become much more competent at using these techniques. The techniques are used much more frequently to assist in projects and so forth. And he's also used these techniques to help actually develop design methods, and I'm suspecting you might hear something about that later on this evening. So it's been a great benefit, and I think Tensar has gained greatly, including another special thing that Andrew does called Tensar Ground Coffee. I'm not sure if anyone has seen these, but I believe it's what's called a blog or something like that. Anyhow, but these are very nice little 5-minute talks that Andrew does about a wide range of their explanations of basic geotechnical topics mainly, normally illustrated with things like buckets of sand and so forth. So that's just something else he's added to bring alive some of the topic that we sometimes see as not a very lively one if we spend all our time looking at computers and so forth. But to see things actually happening makes a big difference. In his copious spare time, Andrew's also written a book about FEA, and I think the next slide might show the cover of this book. There it is, you can see. And I actually have a copy of it here. There we are. I don't know if it'll show up very well beside me here. Not really, does it? It's here. There we are. But Andrew told me I should read this book. So Andrew, I have read it, and I must say it's extremely useful because as giving a background to finite element analysis, it really covers a wide range of important topics. It's not written around any particular FEA program. It's general, which is also one of its very strong points. And in the rest of his spare time, Andrew also gets involved in the development of the Eurocode. I think he's on certainly one of the committees where trying to get a better understanding of using that particular code of practice for geotechnical engineering, which is now I think it's on its second round of redevelopment. Anyhow, sorry, I've been going on for too long, but I think what's important, and I think what you'll soon be understanding, is that Andrew's title of his webinar tonight is typically challenging. Why is Geogrid so difficult to model in finite element analysis? And you might think, oh, it's easy. Anyhow, Andrew, it's now your chance to tell us all about it. So looking forward to hearing your webinar, and the floor is all handed over to you.
Well, thank you very much, Mike, for that marvelous introduction. So I hope I can follow it now with this presentation. Let's just get the slideshow started. Right, so you should see the first slide now, the title slide. Well, first of all, thank you very much to INA IGS for the invitation to talk at this prestigious series of webinars that you've been running, a very successful series with a long list of prestigious speakers. So I'm honored to follow them with this 12th webinar. So entitled, as you see there, and introduced by Mike, why is Geogrid so difficult to model in FEA? So a title that might surprise some of you. According to the manuals that go along with these FEA programs, it is pretty straightforward to model Geogrid. So it might surprise you. So if you found it very easy to model Geogrid applications in FEA, then dare I say that might be something that you're doing wrong, because whenever I do it, I find it very difficult. I suspect that a lot of you have had similar experiences to me trying to model Geogrid in FEA and getting all sorts of issues, getting rather disappointed with what's predicted, finding it difficult to make it run. Some of those pictures you see on the slide there, they'll be very familiar to you. In fact, anybody that's used FEA, those pictures will be quite familiar to you. It's quite a difficult analysis technique to use. You need a lot of care with it to make sure it's being done correctly. So that's what I want to focus on, about the pitfalls of modeling Geogrid applications in FEA. So let's just have a quick look at an overview of what we're going to cover. So first of all, we'll have a look at the Geogrid models themselves. This is really the part that the manuals cover. So we'll just see how the Geogrid itself is modeled. Then we'll apply that approach to some typical cases. And then we'll see that how something appears to be missing, how we're not getting accurate predictions of prototype behavior. And I think that can be explained by a process known as mechanical stabilization. So we'll just have a look at what that is and how we simulate that in FEA. That's what I've been working on quite a lot lately. And then we'll revisit those typical cases by applying the new approach, and we'll see what the result is. So it's useful just to make a distinction between two types of Geogrid applications. So I assume with an IGS audience, I don't need to go into what Geogrid is and so on. I assume everyone's got some background knowledge of that. But there are many applications of Geogrid in civil engineering. The applications on the left are what we at Tensor are often called stabilization applications. They're applications where you have a granular layer with Geogrid horizontally within that layer, but predominantly a vertical load. So it's a vertical load perhaps from a piling rig or a crane in a working platform, or from a wheel on a road, or from a railway, applied to a granular layer with horizontal grid. So essentially the load is at 90 degrees to the grid. So they tend to biaxial type geogrids installed in those. And the other type is what is often called reinforcement applications, where the geogrid is more this type, designed to resist displacement force in one particular direction. So typical applications are slope reinforcement, perhaps for an embankment, maybe a load transfer platform, or a reinforced soil wall, or a reinforced soil structure, such as this. So we're going to look at two typical applications later on. One will be in this area, related to working platforms, and then the other one will be a reinforced soil wall. Although this is called stabilization and this one reinforcement, we'll see that there's still an element of stabilization within these applications as well. And that's what explains sometimes the shortfall in the predictions of FEA compared to reality. So let's look at how Geogrid is modeled. So that if you want to model the Geogrid itself, what do you do? Well, all Geogrid goes into soil. So you measure the properties of the soil in the usual way, and you measure the properties of the Geogrid by testing it in tension in air. So you notice that you test the two materials separately, not together. And then in the FEA model, you introduce those two materials, and the performance is literally the sum of the parts. So it is the mechanical properties of the soil plus the mechanical properties of the Geogrid, and that's how it is simulated. Now, this is the conventional approach, and this is what the manuals tell you to do. Now, regarding the elements used for the Geogrid, then you use a membrane element. So that's an element rather like a piece of carpet. You can't put any compression into it. It'll just rock up. There's no flexural stiffness to it at all. It just has tensile stiffness. So when you pull it, then you get a resistance due to an axial stiffness, EA. So that's Young's modulus times the sectional area, but we never divide them up into the individual components because the cross-sectional area of a geogrid is not a uniform section. So we have to test it over lengths that incorporate sufficient repetitions of the geometry so that we get an overall stiffness expressed as EA. Now, even that on its own is quite complicated to come up with an EA value for a piece of geogrid. So just as an example, here are some EA values, just generic EA values for a particular reinforcement, uniaxial reinforcement product. We'll see that it depends on many factors, this EA value. First of all, it's the product itself. That's obvious. Different products are made of different polymers, and they have different geometrical characteristics and manufacturing characteristics, so they're all different. But even when you know the product, there is not one single EA value for that product. It depends on many further factors, such as the in-service temperature. So polymers behave they have different mechanical properties depending on the temperature. So that's something else that affects the EA value. Also, the load level. So what's plotted in this graph is the EA value against time for the duration of loading or one particular product at one particular temperature, but you still have different EA values depending on the load level. That's because it's a non-linear stiffness. The stiffness actually depends on the load level within the grid. So the lower the load level, this is the lowest 10, we get the highest stiffness. So that's quite important. You can see that the EA value could actually double depending on the load level. In addition to that, the stiffness also changes with time due to creep of the polymer. So depending on the duration of loading, you see the EA value will also vary with time. So given those factors that go into determining the EA value, it's not an easy process just to come up with an EA value. But there are different ways of taking into account all these factors. So that brings us to the constitutive model that you can use for the membrane element. So there are four main options typically available. The most basic is just linear elastic. So that is just one single EA value for the geogrid. So that needs to take into account the product, the temperature, the load level, and the duration of loading. So it's quite difficult to select just a single value that takes into account all those factors. But nevertheless, that is a method that is available. So if you plot load against strain, it will just be a straight line, such as that. If you think the load level is getting close to where the geogrid may rupture, you can adopt a linear elastic perfectly plastic model. So it's the same as the one above, but it will have a limit on the axial load that can be mobilized within the geogrid, above which it cannot take any more load. So any load within the model would need to be redistributed elsewhere. So that might be useful if you decide to do a ULS design of a geogrid reinforced structure. Option number 3 is a viscoelastic model. Now, this is the only one that will take into account the time-dependent creep behavior of the grid. So if you set up a reinforced soil wall, for example, and then you want to simulate its behavior over several years, for example, due to creep in the geogrid, this is the only model that will be able to take into account the changing stiffness with time due to creep or stress relaxation. So you can think of that in terms of it's similar to a linear elastic model in that you are selecting one single EA value no matter loading. So it doesn't count the change with time, but if you select one particular duration of loading, then you can use curves, isocurve for particular. But if you are going to use any of those models, you can obtain the parameter from the geogrid manufacturer. Manufacturer will need to know all this information in order to parameters. So it will need to know the in-service temperature that you expect, some idea of that you to use, but perhaps you can advise that the duration of loading that you're interested in and the approximate load level. You may not know all of this at the start, so it could be an iterative process. You have do this, and then you know the answers. You can go beyond Mimbarnya for revised values in response to these factors here. So that's the conventional way of modeling geogrid. Let's try that out on a typical application. So let's look initially at working platform type applications. So this is what I was calling the stabilization type application at the start. So there's a picture of a typical platform, a platform of granular material reinforced or mechanically stabilized with geogrid. So let's back analyze a plate load test that was performed in the laboratory to recreate a similar type of loading. It's scale, of course, but it's a similar loading of a granular platform, 300 millimeters thick, geogrid, a 300 millimeter square plate that you see there in the middle. over composed hand. So that test form, so this is the data that was recorded from the laboratory. So that one control was done without any geogrid, and we got this low displacement response. And with the geogrid, we see a much improved stiffer and stronger behavior. And you notice that quite early on, at quite a small displacement, there's already a difference between the two. Become important in a second. So tests like these are good to back analyze with FEA to validate your approach. So it's always good to have a control to compare with the geogrid. Then you know that you're getting the soil parameters approximately correct. So the solid line shows the back analysis using FEA of the control plate load test without geogrid. Then what we did is we added the membrane to represent the geogrid using the approach just described, obtain as accurately as we could the stiffness used for this particular geogrid product, and that was the result. Now, this is a typical first attempt at trying to model a geogrid application, I find. Rather all care and effort, accurate soil parameters and accurate geogrid, you see that the sum of the parts, soil mechanical properties, the geogrid, just aren't enough to match what is measured in the prototype. What you notice is that it takes quite a lot of displacement, about millimeters of displacement, before you get any improvement at all. Over here. And that's the fundamental issue with modeling the geogrid in this way, is what we're doing is we're mobilizing a tension membrane effect, as you see illustrated in this photograph here. In order for this membrane, this material here, to support the weight of this membrane here, it needs to deform. It can't stay horizontal and support that weight. You need a vertical component of the tension in order this load here. So that's why we don't see any benefit until we get some displacement. So once some displacement has been mobilized, and by using update coordinates, so when you do this approach, don't forget to update the coordinates so that this tension membrane effect is taken into account. But we're not getting this immediate benefit that we saw in the prototype. What we could do is just increase the stiffness of the geogrid, and some people do this. You can perhaps find ways of justifying that, but one approach is just increase stiffness until you get approximately the correct answer. So that is one approach to go about it. But is that valid, that approach? Like this chap here, we rightly should be very suspicious of these approaches, just adjusting parameters until we get something that matches the result. Okay, the result looks pretty good here, and it's hard to argue against it, but has it faithfully recreated the mechanics of the problem? So, as with all FEA, you need to be very suspicious of the output, even when it does appear to be accurate and matching the behavior in the type. Is it only working for that case? What if we do something slightly different? Is that still going to work? And is that a satisfactory approach, just to double the stiffness until you get the answer that you wanted? So we'll come back to that. But clearly, using the conventional approach isn't quite working satisfactorily. So let's move on to a concept known as mechanical stabilization, and we'll see if that can explain this shortfall in the performance that is predicted by the FEA. So to illustrate what mechanical stabilization is, we've got these devices called Smart Rock that a number of universities have developed. This particular one was by Penn State University. So here you've got a real rock that doesn't do anything special. That's not very smart, that one. But this one, it's 3D printed, and it's smart because it's got accelerometers inside on 3 axes. So that means that you know all the time how it's rotating in 3 axes, but also how it's translating in 3 axes as well. So if we put that into any experimental setup, we know what the individual stones are doing, not just what collectively the whole setup is doing. So this was put in the laboratory in a ballast box setup of half a sleeper or tie on a layer of ballast, with and without a geogrid placed within the ballast layer, a little bit below the sleeper. And then the smart rock was placed just off the edge, the end of the sleeper, just where the geogrid is. So one test with a cyclic vertical load applied. So we could see what the smart rock does without the geogrid and what it does with the geogrid, with the intention of seeing what the geogrid does to the aggregate. So this is the new way of thinking that we're taking here. Instead of just looking at aggregate plus geogrid and what they do, what the sum of the parts is what does the geogrid actually do to the aggregate? Could it be improving the aggregate in some way? So you see the smart rocks placed in this example with the geogrid, and then the ballast was placed over the top, and this is the setup with 2 sleepers or ties and a beam, and a cyclic load was applied here, not for a long time, just sufficient to see any difference in behavior. So there's the output of the angular acceleration of the smart rock on 3 axes. So they're all plotted there, but they're all about the same. And you see over the 500 seconds, so there's about 500 cycles of load. You see how there's rotation, and it actually increases during the test. That was the result without geogrid. And then with the geogrid, you see the remarkable difference in the amount of rotation in the smart rock. So the geogrid is having quite a fundamental effect on the aggregate, in that it's confining it. It's interlocking between the geogrid and the particle resists its rotation. So what happens is that particles interacting with the geogrid are restrained against translation and rotation, as we see here. We also see that through interlock between other particles, this restraint is actually transferred up through the layer. So we get a stabilized aggregate that extends about 30 centimeters above and below if we have aggregate below the grid. That creates a mechanically stabilized layer. Now, in fundamental soil mechanics, you'll know that if you restrain particles against rotation, that increases the of that aggregate. It's for the same reason that an angular aggregate is stronger than a round aggregate, because angular particles interlock better and it's harder to rotate them. So we get an even more enhanced effect here. So we should see a higher shear strength, this material, because the particle is resisted against, there's resistance against the particle rotation or interaction with the geogrid. Never forget that in FEA, you are modeling the soil, the aggregate, as a continuum. So it does not recreate this effect. Even if you model the geogrid as individual ribs, which I've seen some researchers do, that's still not going to recreate this effect in a continuum. Only perhaps by using DEM, discrete element modeling, which is modeling it as a particulate medium, you may recreate this effect. In a continuum, you have to put this effect into parameters, into the input parameters for the material. The FEA will not do this on its own. So what we then did we were searching for this higher shear strength that should occur within this aggregate material. So instead of testing soil and geogrid separately, as you saw at the beginning, why not test them as nature intended together as a composite, to see how they truly perform together and to see if the geogrid actually improves the aggregate. So in large triaxial compression tests, so height to diameter by 1 meter high, so they need to be that big because of the large aggregates that we are testing. We tested aggregates on their own without geogrid, and then we placed a layer of geogrid within the specimen, usually at the mid-height, sometimes multiple layers, but more usually just with a single layer. And then we're measuring, instead of non-stabilized soil plus geogrid, we're actually measuring mechanically stabilized soil properties as a composite. And what we see is higher strength in this area here on the geogrid plane, and it reduces as you move away from the plane until you get to the full influence extent of the geogrid, or at least about 30 centimeters, where the properties